Hi, everyone. My name is Robert Lukovinsky, and my fellow groupmates are Prayuja Telly, David Everly, Christopher Lee, and Tommy Yick. And together we worked on Alzheimer classification using the OASIS dataset. Just a quick overview of what we'll discuss. We'll start off by outlining the problem that we are trying to solve. We'll then go on to discuss previous modeling work that others have done on the topic. Next, we'll touch on our goals as it relates to the problem at hand. We'll then take a quick look at our data set and discuss the pre-processing steps that we took to prepare it for the modeling stage. After that, we'll look at several models that we employed, their results, and the conclusions that we drew from those results. Finally, we conclude by discussing possibilities for future work. And on that note, let's look at the problem. Alzheimer's disease is a neurological disease that causes dementia, which in turn causes loss of memory and reasoning, particularly in older individuals. It is one of the top 10 leading causes of death in the US. While there have been some medical breakthroughs in terms of treatment, there has not been much research done in terms of early detection. The costs associated with treating people with Alzheimer's disease are quite high, estimated at around $320 billion annually in the US presently, with estimates going up to $1 trillion by 2050. While there is currently no way to reverse the effects of Alzheimer's disease, early detection can prevent or delay the development of the dementia aspect, as well as allow patients and caregivers to set up plans of care for future. While the majority of research has focused on making medicines to target the disease, there have been several studies, though way fewer, that have attempted to leverage machine learning models for Alzheimer's prediction and classification. Some examples of these studies include a 2015 study by Edward Chalice, in which his team uses Gaussian process logistic regression to study different brain images. They were able to achieve a 75% accuracy when distinguishing mild dementia from a normal brain, and 97% accuracy of discerning the difference between an individual with amnesia versus an individual with Alzheimer's disease. A 2021 study by Sabramonium and several others utilized ResNet 101 for feature extraction to achieve a 95.3% accuracy using CNN and DNN. Speaking of ResNet, Fulton et al. Performed a study in 2019 utilizing both imagery and non imagery analysis and ResNet 50 to achieve a staggering 98.99% multi class classification accuracy. Our aim was to see if we could create models that would also be able to classify Alzheimer's based off of MRI imaging and to see how our results would compare to those in previous studies. We set out to perform both binary classification, in which we use the MRI images to classify Alzheimer's disease versus non Alzheimer's disease, as well as multi class classification, in which we aspired to classify the severity of the disease. The data was sourced from the OASIS 1 dataset, which is utilized by the majority of studies that we looked at. It has 80,000 MRI images of 461 patients that were classified into four different labeled groups: non dementia, very mild dementia, and moderate dementia. In terms of pre-processing, we first had to deal with the data imbalance. We reduced our dataset such that 488 images from non-demented classes were included and 162 images from each of the other three classes, which gave us a 50-50 split. The multi-class dataset had a much greater imbalance. To deal with this, we downsampled each of the classes with more data points to the size of our lowest class, which was the moderate dementia class. For image pre-processing, we performed grayscale conversion, which we utilized on our normal images. We then had two more sets of images, one with Gaussian blurring and the other with canny edge detection. Finally, we used a 2/3, 1/3 train test split for our modeling.
Hi everyone, I'll be explaining the logistic regression model. So let's jump into the setup of the code. So right now you can see I have two coding files over here. I have downloaded my zip file, which is basically a Kaggle data set. All you need is to download the zip file and keep it as it is where your code is. If you're not, then make sure your path is relatively provided. Once you start running the code, the file folders will get created as data and new data that we'll see in bit. So let's jump into the code. I won't be running the code because it takes a little bit of time to generate the results. So we'll just walk you through the code and finally show the results. At start, we are just importing the required libraries. Then we are unzipping the data set, which is we have downloaded from the Kaggle. We are defining the paths. We have four class in the data set, that is non-demented, very mild dementia, and moderate dementia. Once we have provided paths and collected path, the least part would be then shuffling the data and providing the training and testing of that data. So this is pretty much that. Let me show you quickly the results as we're running on time. We have normal, which is 79.48, blur, which is 79.32, and for Canny, we did get a little bit of less results, which is 69.60. Relatively, I find that all models are not perfectly fitting for the canny, but yeah, that could be something that we can work in future. Along with that, we have plotted it as a confusion matrix for all three, which is normal, blur, and canny. This is one-on-one logistic regression. We have also logistic multi-class. Again, same, import the libraries, unzip the files, provide the paths. Once that is done, put on the training and testing of the data. And we have also Ansible for it. So we'll skip this part and go to the Ansible. Over here, you can see I have plotted all those results again over here. Basically, just to get an idea of EPOS, we have posted that. For normal, we have 80.71. For blur, we have almost 80.25. And for Gani, we have, I think, again, 69 something. Yeah, 66.98% accuracy. And for Ansible, we have a very good accuracy, which is 80.60, I believe. And again, we have plotted the same on the confusion matrix. We also have the results.xls file. This should be a clear idea of which model is doing how much better to get a clear understanding of the models. Rest LDA would be explained by Chris or Tommy, passing forward to them. Thank you.
So for the LDA model, we trained on each pair of classes, which is 6 different combinations. First, we start off with a feature extraction. For each image, the code converts it to grayscale and then resizes it to 128 by 64 pixels. And this is just to make sure that each image has the same dimensions, which lets us flatten them into one-dimensional arrays. And by flattening, we turn each image into a vector of pixel values. And then we perform a normalization. In our code, we do this by computing the mean of our training data and then subtracting that mean from each sample. And this zero centers the data, meaning that the average of the features becomes zero. And after normalization, we use PCA to reduce the dimensionality of our data. This step is applied for training the LDA classifiers and helps by keeping the top 1,500 principal components, which captures most of the variance. This reduction makes the computations more efficient and can improve the classifier's performance by eliminating noise. For the classification part, we use a 1v1 approach. Since we have 4 classes, we train 6 separate LDA classifiers, which is one for each unique pair, as I mentioned earlier. Each classifier is trained on a 2-class problem using the features from the PCA reduced data. And the LDA part of the code computes the within class scatter and between class scatter matrices, and then it finds the optimal projection direction that best separates the 2 classes.
For the next approach, we use an ensemble model that combines linear discriminant analysis, logistic regression, and k-nearest neighbors. For LDA, instead of training from scratch, we load pre-saved parameters, including class means, PCA projections, and weight vectors. It works in a 1v1 setup with 6 classifiers, each comparing 2 classes. The final prediction is based on majority voting. And as for logistic regression, it follows a similar approach, using pre-saved means, standard deviations, and weights. Data is normalized, passed through a sigmoid function, and classified using majority voting across 6 classifiers. For K and N, we use canny edge detection to highlight structural features. Then the model finds the 5 closest matches in a training set and assigns a class based on majority vote. Instead of just relying on one model, we combine all 3 predictions using a weighted voting system. Each classifier's output is converted into one hot vector, average, and the final class is the one with the highest score. By using multiple models, we leverage LDA's class separating feature, logistic regression's decision boundaries, and KNN's ability to recognize structural patterns. By loading pre-trained parameters, we cut down processing time significantly. And since each model has strengths and weaknesses, the ensemble approach provides a more balanced and accurate classification than any single method alone.
In analysis of results, we found that in all cases, normal and blur images had the best accuracy. The logistic models were slightly more accurate than the linear discriminant analysis. All models are relatively similar accuracy in the range of 77 to 80%. And then the addition of the ensemble for the logistic and the LDA both slightly improved accuracy, but likely not to a degree that is statistically significant. And then in all models, the canny images had significantly lower accuracy for classification. In conclusion, we found that the logistic regression models slightly outperformed the LDA models, and that the addition of the ensemble did slightly improve accuracy, though likely not enough to be statistically significant, and that canny edge detection on the images did not help to boost the accuracy, actually significantly reduced the accuracy of all models. Future works, just some areas that we could research further, particularly in using images in real dimension, because we pre-process this data in such a way to make our computations easier and for data storage to be a bit easier, but it's possible that with that lossy compression, we may have lost important features in the data. Also, this data was only a single data set with slightly over 400 subjects, so repeating this study in a data set that involves a larger, more diverse population may provide a different result. Thank you.